So let me talk about the field first of all. Okay, so field is a ring. First of all, it should be a ring. Okay, and every element of the field and every element of a field should have an inverse of a field will have an inverse under multiplication under multiplication. Should have an inverse under multiplication. Okay, so some example of a field are take real number is the field, rational number, and so on. Okay, so on. So these are some example of fields. Okay, so before now we'll go through with the definition of vector space. Okay, so in vector space we have two operation. Okay, we have two operation. One is addition and one is scalar multiplication. Okay, so first of all we have to take a non-empty set V. Okay, so I'm taking a non-empty set. You should be very sure with that it is empty or non-empty. So if it is empty, you cannot define a vector space. So first of all, it should be a non-empty set. Okay, it's said to be a vector space over a field. So we are talking about a field over a field. Okay, on which field we are defining, we have to be very sure that on which field we are defining, because a same vector space on another field, it might be a vector space or it might be not. Okay, so we should be very careful about the field. So a vector space over the field, first of all, it should be an abelian group. V plus under addition, it should be an abelian group. So whenever you prove a vector space, first of all you have to prove that it is an abelian group. After that, we have a scalar multiplication. So I have taken one scalar here. So scalar multiplication, let us define the scalar multiplication. Suppose I donate the scalar multiplication as dot. Okay, so first of all, you remember V should be an abelian group under addition. It should be an abelian group under addition. So I'm defining a scalar multiplication. So I'm taking the field, this is my field, cross with the vector space, it should be sent to the vector space. How you define this? This is defined as, I take an element from the field. So the element from the field, I'm taking alpha, and the vector from V, I'm taking as small v. So this, I am defining this as alpha V, and this should belongs to the vector space for all alpha belongs to the field, for all the scalars, as well as for all the vectors belong to the vectors V. For all the V belongs to capital V. So after this, it should satisfy the following conditions. Okay, so this one is satisfy the following properties. It should satisfy the following properties. So the first property is that you take two vectors. Okay, you take two vectors. So I take v1 plus v2. You multiply with a scalar. So scalar multiplication. So if we can show that this is alpha v1 plus alpha v2 for all v1 v2 belongs to v and alpha belongs to the field. Okay, so if we can show these two are equal, next property is that you take the sum of the two scalars. So I take alpha plus beta, and you take one vector v. So if we can show that this is alpha v plus beta v for all v belongs to v and alpha beta belongs to the field. Okay, so that is your second property. And the third property is that you take the multiplication of two scalars, multiply via vector. If you can show that this is this for all v belongs to v and alpha beta belongs to the field. Number 4 is 1 into V. If we can show this is V, for all V belongs to V, then it is said to be a vector space. So first of all, to become a vector space, you should remember that first of all, it should be an abelian group under addition. It should be an abelian group under addition. Abelian group. Then it should have a scalar multiplication property. Okay, so it should satisfy these 4 conditions. First of all, it should be an abelian group, and after that, it should satisfy these 4 conditions. If they satisfy these 4 conditions, then we say that it is a vector space over the field F. Thank you.